Hi, I'm Caesar. It is actually the next chapter or the next part of our previous part, which is the part 2 of our computational fluid dynamics theoretical series. In part 2, we discussed about the uh, simulation of transient heat conduction, one-dimensional, using just Microsoft Excel. And this is actually just like the extension of this part, so we will do the basically the same thing, but we will do it using the MATLAB. So why I use MATLAB? Because it is just very simple and well known, especially for engineering applications, so I hope you can follow it easily and give you a better idea about our finite difference method we discussed previously. So I hope you watched the previous part of this Excel thing, so I don't have to explain it again much and focus on the MATLAB. So it will be a simple code, but it will not be the simplest, so I hope you get just a little understanding about MATLAB previously, especially for the for function, and maybe the other is just like the normal operations such as the variable thing, and okay, let's just jump into it. So to start our code, basically I just use the CLC clear all just to make sure that everything clear, and also I will close all because at the end of this code I will make some graphs, maybe just one graph for temperature versus the distance, so I will close all so I don't have to close everything once I want to run a new simulation. So first, let's define our inputs. As we know, the inputs will be defined here as the material properties. Maybe this one, I will just retype it like the density or rho, or maybe the dimension first. The dimension or the length of the rod will be 1 meter. Oh, sorry. And the thermal conductivity 45 watt per meter degree Celsius, so everything will be in the SI unit. The density is 8000. Then the CP or the heat capacity is 460. So again, it is just random numbers from the internet, so we will just focus on the numerical method. Then we set, or we first want to calculate our alpha number. Alpha is, forget the alpha, is K divided by rho CP. K divided by rho and CP. Okay, then we define our boundary conditions input. Okay, so the temperature at the left side will be 100 degrees Celsius. Then temperature on the right side is 30 degree, and the initial will be 30 also. So I basically just want to input here, so every time we want to change it, we don't have to search it on the detail of the program, so we just change here and everything will be changed. And I think that's all for the inputs. Then we define our time step setting. So as previously defined, our time step will be the like the column. So let's say we want to divide the time into 20 steps. So let me just define first the number of time step. Let's say n, because we will use the n as the time identifier, like this small n. So I just use the large n. It is obviously depends on your preference, as long as it is consistent. And let me just give the comment so I will not forget. Time division, let's say, or time grids maybe. Then I will also define the last time, or the time when the simulation will be finished. Let's say you will simulate it 60 seconds. Just define it as the end time. Then the dt or delta t, it will be easily calculated from dt divided by n. So I don't have to calculate it one by one, for example, like this, 60 divided by 20. It will just change whenever I change the, let's say, the number of time grids, or maybe the end time. Or you can change it. For example, you want to make the delta t the inputs, so you can get the number of grids. It is up to you. You can put it the delta here and the n value here. Of course, it is up to you. And then I want to define the t, or time, equal to it will be like a vector from 0 with the step, or the like the delta t will be delta t, obviously, for 0, from 0 to t. Okay, so it just like define the time vector. So I just maybe run it. So okay, this is our time. So it will be 0, 3, 6, and so on and so forth, with the delta t of 3. Okay. Then let's define our special discretization, or special meshing or grading. I will use the I as the total number of special discretization, because I will use the small I to define the space identifier. So I will just use the large I. So it will be 10 divisions here. Okay, then for the dx, I will calculate it the same way as the time. I will just use the L, or the length total of the rod, divided by the I. So the x coordinate, I will define it the same way as the delta time, from 0 to L. Let's check again. Here we get the x from 0 with delta x 0.1 all the way through the L equal to 1. Okay, then I think we finished for the definition of the grading. Then we define our temperature matrix. So I will define it for I equals to 1. so it will be a little bit different here. I think I made a mistake in the previous video. It should be from 1, not from 0, so it will be divided by 10, but it's okay, this is the same idea. For I equal to 1, with from I equal to 1 to I plus 1, so it will be 10 plus 1, so it will define the last column. So the t I comma 1 equals to t initiate, or t ini, comma n. So it will make a new matrix, or a new matrix of temperature or large T with the initial value of T in ini. So I'll just run it and check the T matrix. So we see here everything is 30 in the in every single data in this column. Okay, I hope you still follow me here. So let's just define our S value, this one. The S value here, S is equal to alpha times delta T per delta X square. So I will define it here. S equal to alpha, so okay, alpha times delta T divided by delta X square. Of course, this sometimes I just use too much bracket. I sometimes feel not confident with only one bracket, so yeah, okay, it's just my preference. Then okay, we already defined the S, so we can actually calculate or input our equation. So we basically will use the forward time central space here. So the idea is exactly the same as the previously discussed. So we will calculate every row with this equation, then moving from first row, second row, and third row all the way through all these columns. Or we calculate the spatial equation first, then we calculate it for every time calculation. So the time will be outside for the algorithm. Let us just write it down. Let's say for the n equal to 1 to n minus 1, so the outside code for the 4 is the time, or the n identifier, and the inside, or the like the next calculation will be for the spatial discretization, or for I equals to 2, because for I equals to 1 we already use it as the initial condition. For I equals to 2 to the I, because the last column is I large I. First, let's define our boundary condition, or maybe first we must input our left boundary condition, which is T1, n plus 1 equals to T left. So 1 here it identify as the the leftmost of the domain or the I equals to 1, which is the leftmost part of the domain, for every n plus 1. Yeah, so for every time for n equal to 1 to n plus 1, n plus 2, and so forth will be the same value, which is the t left, or 100 degrees Celsius. It will be the left boundary condition. Okay, let's just go to the most important equation, or the our main equation, which is this forward times central space. We just type it exactly the same: I comma n plus 1 t I comma n plus 1 equal to tin equals to t I n. So we actually made this equation like this for a reason. So if we input it in the programming language, for example for this MATLAB, it will be much more convenient. And the 2 times s time the bracket, sorry, which t I minus I minus 1 comma n, then plus the t I plus 1 comma n minus 2 times t I comma n. Okay, this is our FCTS equation. FTCS, FTCS. Okay, the last thing we must input is the right boundary conditions, which is the right one, or the leftmost part of our table, or our grid, will be I plus 1, right? Because we write it here for I to I plus 1, comma the n plus 1, with the same reason as the first boundary condition, will be equal to t right. Yeah, it will be the right boundary condition. So it will be our initial condition. I just give it here. Okay, and we will end the calculation for the special calculation here, and then we will end it for every time calculation. So the outside part here is the time, and the inside part will be the space. It's just actually the same idea as this calculation. Okay, I think you get the point. I hope you get the point, because this is the most important part of our code. And the last touch will be our post processing. It will be not very advanced. I just want to make a plot of x with respect to t, with the x-axis will be 0 to L, and the y-axis will be, let's say, 30 to 100. Okay, then I will give the label of the x coordinate as length, let's say length like this. Okay, and the y label will be temperature. Okay, just like check this, and I hope there's no error. And why is it so long? Nah, this is our graph here. Very coarse, looks like, unfortunately, but no problem. We actually solve it. So this is the lines will display the temperature over the distance in every time step. So we will check also this one, this table, which is exactly the same as our Excel table here. This one, sorry, this table, but it will be in that direction. So actually it is not a problem which direction will be the Excel or the table. So just because this is like only for, as long as our table is correct, it will be correct. And I will close this, and maybe I will make our simulation or our curve smoother by using the number of spatial discretization here. Let's say 60, so the delta x will be have a better value. Or maybe I just delete this semicolon, so I will show you the value of the delta t and delta x, and also the s, so we can see the value. So the delta x is 0.01, so we get the smoother curve here. Okay, or maybe we want to make the time discretization also smoother here. Let's see. You see here the dx dt, it's smoother, so we have more of that stuff, that curves. Maybe I will make the time longer, so we get the longer distribution of temperature over time with maybe 200. I just guessing some number here. And yeah, very smooth and better distributed. Or maybe I want a longer time, 6000, let's say. And whoa, what happened? Yeah, it's called the numerical instability. So if we just input some values which is not correct, I can say, for the delta t and the delta x, the simulation will just get blow up. And this is governed by the delta x, delta t, and the value of s. And we will discuss it later in our discussion about the stability, and we will find what makes the simulation blow up. And this is actually very important topic in the numerical simulation, and I will make the dedicated video for that topic. So I think that's all for our tutorial today. I hope you get hands-on experience on this, so in the further discussion you will get the better idea of what we discuss. So thank you for watching. I hope you like this video, and please subscribe to this channel if you like this video, or maybe please comment in the description below about maybe some question about this video, or maybe you have some request about the next video. Thank you for watching.